Hello guys, welcome back to Maison African Motives. Still on Mechanotechnics and for working on metal cutting machines. We've got the question here on question number 7 from our March 2023 exams, where we are given the fig 5 shows the setup of a cutting tool held in the tool holder of a shaping machine. The ram of the shaping machine is a mass of 150 kgs in operation with a cutting stroke length of 200 millimeters. The total work done during one cutting stroke is equal to 120 joules. Take note here, during a one cutting stroke. And also the coefficient of friction between the ram and the slides is 0.3. So this is what we have on our diagram. The clamping screw, the distance is here 40 millimeters, 40 millimeters, 50 millimeters, and also the cutting force. And we've got the 1000 Newton here. So the first part of the question was to calculate the following: the work done to overcome, take note, the work done to overcome the friction between the ram and the slides. 3 marks for that. The work done. What is the total? What is the work done to overcome the friction? So meaning to say we are talking about the work done to overcome friction, which I'm going to just write as WDF. That is the work done to overcome friction. In our normal way, we understand, or we know that work done actually is a product of force times distance, which some of us write as S, force times distance. But if you are to check here, we are talking about the length, which is the stroke length. So which means we are going to talk about the frictional force, since it is the work done to overcome friction. So it is going to be the frictional force that we are going to work with here. And the distance, this one is going to be our stroke length. So here we are going to refer to the stroke length. All right, so let's take our information and see how we can have this. Take note here, we are given first part, the ram that has got a mass 150, the stroke length 200 millimeters. Okay, so we have got the mass of 150. So let's just have our information, the mass of 150 kgs at a stroke length of 200 millimeters, which you convert to meters, divide by 1000, that's 0.2 meters. Also, we are given the force. Let's just take here the total work done. That is during one cutting stroke is equal to 120 joules, and also the coefficient of friction between the ram and slides 0.3. Okay, so we've got the total work done per cutting stroke here, which is I'm just going to write as total for T, which is 120 joules. And also the coefficient of friction is 0.3 at that moment. Okay, with this information, how can we obtain the frictional force? Because we do not have, we have got only the stroke length. Because remember, we said here our formula now is going to be like this. The work done, let me just have it as a separate part. That's question 7.1. So our 7.1, the work done due to the friction or to overcome this friction is going to be the frictional force. So we are going to work with the frictional force times the stroke length. So here we've got the stroke length, but we do not have the frictional force. Okay, if we are to check before or on the information that we have got the coefficient of friction 0.3. And we know that the coefficient of friction can be taken from the frictional force, which is our horizontal force, over the normal reaction, which opposes there to the mass times the gravitational acceleration. So meaning to say, with this formula, we can actually calculate our frictional force, because this is same as over 1. So we can simply cross multiply. That means we can have our frictional force as the coefficient of friction times, so this is going to be the coefficient of friction here, times, if you cross multiply these two, times the normal reaction, where we know that the normal reaction is taken from mass times the gravitational acceleration. So this is going to be opposite. So we're going to use the mass times gravitational acceleration, which is 9.81 meters per square second. So this is the formula that can give us the frictional force in this case. So with this formula, I'm just going to insert the values that we have. So our frictional force is going to be the coefficient of friction. The coefficient of friction, that's 0.3 times the mass times gravitational acceleration, this one, which is the mass of 150 times the gravitational acceleration of 9.81. So this is going to give us the total frictional force that we are having. So the frictional force here is going to be, that is going to be 441.45. So this is in Newton. Remember, friction is measured in Newton, but this is not the one that we are asked on our question. The question is about the work done to overcome this friction that we are talking about here. So meaning to say, we are going to use this now, the frictional force times the stroke length. So we're going to substitute this value to calculate our work done to overcome that friction. So our frictional force, remember, we got our frictional force, which was 441.45. So this is 0.45 times the stroke length, and our stroke length in meters here is 0.2. So that's 0.2. So this is going to give us 88.29. So that's 88.29 in joules. So remember, we are talking about work done. So work done is measured in joules. Okay, so that is how we can play around with this information to get or to obtain this part that we are talking about, which is the work done to overcome the friction. Okay, let's check the other part of the question. We are given the other part of the question on the next page here. On 7.2, that is to calculate now the cutting force exerted on the cutting tool. On the cutting tool, we need the cutting force there. All right, let's check what we have on the cutting tool. So on the cutting tool here, all right, here is our cutting tool, guys. If you are to check here, we've got the cutting tool, this one. All right, so there is a force here, the cutting force. So you can write this as they can write this as F1, F2, or whatever that you want. But here I'm just going to write as FC. So FC for me represents the cutting force, the one that you're supposed to calculate now. All right. So which information can we use to obtain this FC that we have, the cutting force, this one? Okay. Remember from our formulas, okay? Remember from these formulas that we had, if you take, if there is work done and the distance, we can actually have the force. Remember, we need to calculate the cutting force. So if we have got the work done, force and distance, we can be able to calculate force, because we are saying work done is force times distance. So meaning to say, we can make force the subject. From this, we can divide by length, meaning to say work done divided to the length or the distance gives us the force. Okay. But this time, which type of work done are we going to use? Remember, we are talking about the cutting force, which is FC. So meaning to say, we must have the cutting work done corresponding to the stroke length. The L is for the stroke length. That one does not change. So where are we going to have the cutting work done? Remember, before we calculated the work done, that is to overcome friction. Now we need the work done, that is the cutting work done. And before, again, we were given the total work done. So if we are given this, remember, from the total work done, it is the sum of these two other work done that we are having. So we are saying the total work done actually is equivalent to the work done against friction that we had before, plus the work done, which is our cutting work done in this case. So these two added together, they give us the total work done. So meaning to say, we can calculate this cutting work done, which is WDC. So you can have transpose this. So that would be minus WDF represents the work done at the cut. That is our cutting work done. So meaning to say, if we are to substitute the total work done minus the work done to overcome friction, we can have our cutting work done. So our total work done in this case is 120, whilst our work done to overcome friction is 88.29, this one. So 120 minus this, okay? So that will be 120 minus 88.29, okay? So this is going to give us the cutting work done, okay? So like I said, that's minus 88.29 from the calculated value that we had before. So we are going to have our WC. So the work done at the cutting is going to be 31.71 joules. That is our cutting work done. So with this cutting work done that we have and the stroke length, we can be able to calculate the cutting force. So our cutting force, like I said, I'm going to write this as FC. So our cutting force is going to be the cutting work done, which is 31.71 joules divided to the stroke length. The stroke length is not changing. We still have our stroke length L as 0.2, the one that we had before here, 0.2. So this is not going to change. So we're going to divide by the stroke length, which is 0.2. All right, so divide by 0.2. This gives us the cutting force. Like I said, you can write this cutting force as F1, some they can use F2 and so forth, no matter the way that you understand. So this is going to be 158.55 in Newton. Remember, this time we are calculating force. So that is our cutting force, or we can just write as F cutting. All right, F cutting is equal to 158.55 Newton, like that. Okay, so that was our question 7.2. Let's check the other part of the question. From the same diagram, same information, now we are asked to calculate or to determine the forces exerted on the two contact points A and B. Take note. The forces which are at the two contact points A and B. If the clamping force in the clamping screw is 1,000. Take note, we have got the clamping force in the clamping tool, which is 1,000. And also test your answers. That is what you are given in this case. All right, so we've got a total of 9 there. All right, how can we have these forces at A and B? Okay, at A and B, this is what we have here. Okay, let's get back to our diagram. Okay, sorry for that. Okay, I need this diagram. All right, this is our diagram here. So we need this part. This is what we are going to work with. Remember, now we calculated this value here, this one. The force, the cutting force, this one, 158.55. Meaning to say, we have this value here. Okay, let me just try to remove something here. So we calculated this value direct, our FC, or the cutting force this time. We calculated this. So we are going to work with our FC of 158.55 Newton. All right. So the question is, guys, we are supposed to calculate the forces which are acting at the points A. At A here, there is a force that is acting here. At B, there is a force acting at B like this. Okay. So if you are to consider from the cutting tool that we have, from this cutting tool that we have, if you are to consider properly, you are going to see that, guys. Let's see this our diagram properly. Okay, let me have this 7.3. I want us to have our diagram properly. If you are to consider from this cutting tool, just because it's a sketch, guys, but I just hope it's going to be clear. This is what we have from this cutting tool, something like this. Okay. There is a force of 1,000 here, which is acting here like this, okay? 1,000 here, direct to this point. So this we are going to actually present it. It's a point load. This one is actually a point load. Same with the cutting force at the end point here. This is a force again. So meaning to say, we have got the force here, FC. This is where we've got our cutting force, which we got 158.55 and so on. And also before that, okay, let's consider stage by stage so that I don't confuse you guys. Let me work it stage by stage. At the cutting force at FC, if you check from this point up to this point, this is the distance that you are given here from this point to this point at A. So at A, here, we have got a distance in between that you are given of 50 millimeters, okay? That is at point A. So this corresponds at A. So at A, we are supposed to calculate actually the force at A. So it's supposed to be like this. So it's a force that you are supposed to have at A. So we do not know this. We move another distance again, 40 millimeters to the force of 1000, which is in between this one. It's at 1000, which is in between the 40 milli. So in between, if we move a distance of 40 millimeters, there is a force that is a point load acting at that point, which is the 1000 Newton after the distance of 40 millimeters. We move again another distance from this point to this point, 40 millimeters. From this point to this point, 40 millimeters. Where are we now at the end? We are at the point B. So a B like this. This is where we are now at B. Do we still have any other force acting? We do not have. So these are all the forces acting on our cutting tool, this one. These are all the forces acting here. With these forces, how can we calculate now the force at A and the force at B? So using our law of moments, we are going to have this simply on a simple diagram like this, the one that we understand. So these are simply point loads, FC and the 1000. So we are going to have our FC at the end here. So this is where we have our cutting force at the end, just in a diagram that you understand. So this is our FC, which we calculated 158.55 Newton. From this point, that is where we have a support at A. So this is at A here. From this point to this point here, that is 50 millimeters. This is the one that you have in between FC and A, 50 millimeters. All right. From A, we move 40 millimeters to 1000 Newton. So here we are going to use or to move 40 millimeters, 40 millimeters until we are at the corresponding force of 1000 Newton here. This is the one that corresponds 1000 at this point. So we've got 1000 Newtons. From this force that we have, 1040, then to B. So we're going to move another distance, 40 millimeters back to the point, to the support, which is at B. So this is our diagram. So this other piece does not even matter, this one. We can just conclude, say, there's nothing there. It does not even matter. So the question, how can we calculate now the force at A and at B? So using our law of moments, I'm going to start with A. Taking moments about A. So taking moments about A. So if we are taking moments about A, that means we are going to calculate for B. So if you consider, remember, this direction is clockwise and opposing this now is anti-clockwise. So if you are to check B as it moves back to A, it's moving in the clockwise. B is moving this way. It's anti-clockwise, sorry. That is anti-clockwise. Sorry for that. B is moving this way to A, which is opposing anti-clockwise. So B is in the anti-clockwise. Back to the point A. Also, if you check the FC, this one, as it moves back to A, this FC as it moves back to A, is also anti-clockwise. So we've got anti-clockwise, anti-clockwise. The 1000 as it moves back to the A here, this one is in the clockwise. This is the direction for clockwise, okay? So depending with the formula that you have written before or that you're going to use, you can formulate here. I'm going to use the sum of the anti-clockwise moments is equal to the sum of the clockwise moments, which is the sum of the anti-clockwise moments I'm referring to. Remember, I said B back to A is anti-clockwise, so it's B back to A. So you consider the distance of B to A. So the distance between B and A, it's 40 plus 40. This whole distance here, 40 plus 40, which is 80. So there's a distance of 80 millimeters. So that's the force at B times the distance to A of 80 millimeters. We still have another anti-clockwise that we mentioned, the FC. So we're going to add the anti-clockwise from FC back to A, which is 158.55 times the distance back to A of 50 millimeters. All right. Do you still have any other anti-clockwise? We do not have. So you're going to move to the clockwise now. The sum of the clockwise, there is only one clockwise that we have at 1,000, this one that I mentioned here. So it's 1,000 back to A, which is 1,000 times the distance of 40 millimeters. In between 1,000 and A, there's a distance of 40 millimeters. All right. So with this information, guys, we can be able to calculate the force at A, the force at B from this information. And using the same information, if we use it again, we can be able to calculate the force at B. So at A, so this is going to be 80B plus, if you combine these two, you're going to obtain 792, that's 7927.5 is equal to 40,000. So this will be 40,000. Transpose this to the other side of the equation, so it can be a negative 7,927.5 because it's a positive here. So you're going to subtract. So that means I'm going to remain with 80 B, which is equal to 40,000 minus this value. We are going to obtain 32,072.5. So divide by 80 both sides, by 80 both sides. This gives us the force at B, which is going to be 400. So we're going to obtain 400,906,90625. So it's going to be 0.6. This is actually supposed to be 0.625 Newton like this, okay? So you can actually round off to 3 decimal place. If you have your final answer, you can just have this to 3 decimal place, which is going to be 400,906 in Newton. Okay, so this is what we are going to have at B. This is the force that we are having at B. So using the same way or the same calculation, since we are supposed to prove our answers, so I'm not going to use this information that I'm having here. I'm going to take back to the I'm going to work from the diagram because we are supposed to test our answers later on. So we're going to the diagram again. So from our diagram, this is no longer anti-clockwise because now we are relating another part which is different from this. Okay, so this time I'm going to consider my moments about B, this time about B. Okay, so I'm going to take moments about B. So taking our moments about B. So let's see what you're going to have. If you check about this point B, A as it moves back to B, this is our A as it goes to B, this direction. And this direction is clockwise. This is how our clock moves. So this is clockwise. And if we check 1,000 as it moves back to B, this direction is anti-clockwise. It's moving like this. So this is in the anti-clockwise. The same with FC as it moves back to the B, it is in the anti-clockwise. Okay, so depending on the formula that you're going to use here, I'm going to, since I just want to take advantage of A to be my first part of the equation, so I'm going to take clockwise for A. So it's clockwise moments should be equal to the sum of the anti-clockwise moments, which is the sum of the clockwise, that is from A to B. There's a distance of 80 millimeters. So it is going to be force times distance, A times 80. That is what we have. Do we still have other clockwise? We do not have. This is the only clockwise that we have. So we move on to the anti-clockwise. Okay, we can start with this one that is near B, which is 1,000. So 1,000 back to B, there's a distance between 1,000 and B of 40 millimeters. So it's going to be 1,000 times 40. So we are going to have 1,000 times 40 here. Plus, we still have another clockwise, anti-clockwise, which is FC as it goes to B. So it is going to be 158,55 times the distance. So this times the distance from FC here back to B. We are considering the whole distance from FC to B, which is 80 millimeters plus 50. This or 50 plus 40 plus 40. So if we add everything there, this is going to give us 130. So that is 4 times distance. So we are going to multiply by 130. All right, so that's it. Combine everything on the right-hand side. This is going to give us 60,611,5. So divide by 80 both sides to find the value of A. So you can divide by 80. So our A is going to be 757,64375 in newtons. Okay, so of which you can just write this to 3 decimal places, 757,644 in newton. That is to 3 decimal places in this case. All right, but do not forget that we are also told here that we are supposed to test our answers. So take note, we are supposed to calculate the forces exerted on the 2 contact points A and B, and also test your answers on the last part. Test your answer. So to test, how are we supposed to test how can we test our answers? That is the question. If you take from our law of moments, we can use the forces now to say the sum of the upward forces A and B, these are the upward forces, our supports, is supposed to be equal to the sum of the downward forces, these ones which are going down. All right, so this is how we can prove whenever we are dealing with forces in this case. All right, so you can prove this to say, or we can test this. So to test here, we are going to work the sum of the upward forces, so you can indicate an arrow going up, is equal to the sum of the downward forces. That is the upward forces. These ones are the ones that are facing up. That is A and B. So if we add A, so I'm going to use the original values. A, which is 757,64375, plus B is our support. I'm using the original value, 400,90625, must be equal to the downward forces. These are the ones which are facing down, our point loads, and our point loads are at FC. This is the one for FC, this one, and the 1000. So these two are the ones that are going down. So we add these two. So it's 158,55 plus 1000. So this is going to be 158,55 plus 1000. We are supposed to obtain the same answer if truly we calculated properly here. So this is going to be, here I'm going to obtain 1,158,55 Newton, which is equal to 1,158,55 Newton if we simplify properly. So this is how we can test our final values in this case. Okay, so these are the typical questions, guys, that we might be given. So that was the last part of our question of this typical cutting machine process that we have. So we have to just work with more questions, guys, to understand how do they ask and how are we supposed to relate from the diagram that we are given and with the information that we have. But I think this is clear. We just have to work with more questions to understand your diagram, take time when you are given a diagram. Most of us, when we just see a diagram, we are already confused. We are nowhere on answering that question. No, any question that has a diagram, that's the easiest question because it has information from the diagram. So you can take advantage of that. Okay, anyways, guys, we shall see more questions in our next classes. Let's continue to revise more question papers in preparation of exams which are ahead of time. But for now, that's it, guys, from Mechanotechnics African Motives. Till we meet again.